Okay, so previously we talked about PD control and PI control, and we saw this behavior. We saw that increasing the integral gain increases the overshoot, but makes the system's response faster, and it also removes steady state error. So the benefit of PI control is that it removes steady state error. The drawback is that it can lead to large overshoot. In the response, and if it's improperly designed, it can lead to instability. Let's do skill check. Why is integral control usually used in a system? A, lower the amount of control effort. B, reduce overshoot. Or C, decrease steady state error. It is used to decrease steady state error. Okay, now if we use all of these terms together, we are going to have a PID controller. So a PID controller is when we have proportional, integral, and derivative terms. So we had this response with proportional control. With PD control, we got this. We had steady state error and a spike here. PID control is the best of two worlds. It has PD and PI. It removes the steady state error. It reduces the overshoot. And it has the behavior we want. So, summary of what these terms do. The proportional term provides a rapid response to control errors, but it increases overshoot, and if it's too large, the system becomes unstable. The derivative term decreases overshoot, but it slows down the response. The integrator term eliminates steady state error, but it increases overshoot and increases the oscillations. This table summarizes what each of these gains would do, increasing Kp, increasing Ki, and increasing Kd. How do they affect percentage overshoot, settling time, and steady state error? So, in what cases would a full PID control be needed in applications? When is it that I don't use P, PI, or PD? A, to improve both the steady state error and remove oscillations in the output. B, to lower the amount of control effort needed. C, to control a nonlinear system. We didn't talk about nonlinear systems. B is not correct. We don't necessarily have a smaller or lower amount of control effort or control signal. So it's A. It improves both the steady state error and removes the oscillations. Okay, so we talked about PID controllers and why we use them. Now, how do we design them? How would I know what the values of proportional gain, derivative gain, and integral gain should be? Two guys, Ziegler and Nichols, John Ziegler and Nathaniel Nichols, in 1942, published a paper from industry and what they experience in industry. And it's a very interesting method to tune your PID controller. The tuning rules assume that the plant is a first order system, but the method surprisingly works if your plant is not a first order system. So what Ziegler-Nichols method creates is a quarter wave decay, which is an acceptable result for some purposes, but it's not optimal always. So it's a good method, but it's not necessarily the best design you can have. It depends on the application. Okay, so this is the way the method works. You start by using only the proportional control. So you turn off the derivative and integral control. You increase Kp from 0, gradually you crank it up until you get a response that is oscillatory. So you just have constant oscillations. Then you write that down, you call that KU, or ultimate gain. And you measure the period of your wave or your signal, you call that ultimate period. Your system, your closed loop system right now, when you have this ultimate gain and you have oscillations, only oscillations, that is, your system is marginally stable. And if you increase your gain, you keep increasing your gain, you're gonna have an unstable system. Okay. Now that you have KU and PU, the ultimate gain and ultimate period, Ziegler and Nichols suggest this chart or this table. They say if you want to design a P controller, a PI controller, or PID controller, I'm going to tell you what the values of your parameters should be based on this KU and PU. So if you want to design a PID controller, KP should be 0.6 times KU, TI should be PU times divided by half, and TD should be 0.125 times PU. Let's see an example. Imagine you are a control engineer working at Tesla. Your team is tasked to design a steering control system for new Model Y. Your team has previously found the plant transfer function G, so you have the transfer function of your system written this way, and B and C and omega n are provided. You want you have decided to implement a PID controller for the closed loop system. The question is to design this PID controller, to find the correct gains for PID controller. So we plug in these values to our system. We first imagine we don't have the Ki and Kd, and we only have Kp, only have proportional control. We start increasing this gain until we get an oscillatory behavior. So we can also use Rath-Horowitz. As you know, Rath-Horowitz can tell us when the system becomes marginally stable. So the value that Rath-Horowitz criterion provides for us is 885.5 for the gain. So the value of proportional gain or ultimate gain is 885. Now we use the values that Ziegler-Nichols table suggests us to find Kp, Ki, and Kd. And that's how we use Ziegler-Nichols to tune a PID controller.